So the first encoder that we'll look at is what we call an absolute encoder, and this shows you one that's set up in binary. So what we did, this is where we combine sensors. We'll look at later on what we refer to as a through-the-beam sensor, which is a optical photoelectric sensor. Where what we have is we have a transmitter that sends light, and then we have a receiver that detects light, and then what we do is we're shooting a beam between the two. Now what happens if something in here, opaque object or something that doesn't let light pass through, if it comes into the center here, of course, then the receiver doesn't receive any light. Pretty simple setup. Okay, you understand that? So what we're going to do is we're going to come over here and we're going to establish what we're going to reference to, and then we're going to put these transmitters and receivers through here. So this right here is transparent, so the light can pass through it. Well, when this unit right here turns, then what's happened is the light is going to be blocked on this one and pass through with that one. That makes sense? And then when this wheel turns, I'm moving, well, when the wheels turn right here, this one would pass through, this one would be blocked, and these two right here would pass through. That makes sense? Okay. So if we was looking at the output, we'd say, okay, if it got light through, then we could say that represents a binary 0. If it don't get light through, that would represent a binary 1. Okay. Now the way we count in binary, 0, that would be a 0. This would represent a 1. This would, I say represent, it is a 1. This is a 2. This is a 3. This is a 4. This is a 5. This is a 6. This is a 7. This is a 7. This is an 8. This is a 9. This is a 10. There's 11. I'm going to write, that's 12, 13, 14, and 15. You see that? Now this is binary, and a lot of people call this the 1248 code because this is the decimal weight that binary holds. It goes 1, 2, 4, 8, 16, 32, 64. And then what we do is we just look at the weight that this column holds. So let's look at this one right here. This holds a weight. If it's a 1, we add it. If it's not a 1, we leave it off. So we follow this column right down here. Look at this. So I'd add a 1, and then I follow this line down right here. I got off. And this would be a 4. If I add these two together, then that would come up and give me a 5. So this is the binary equivalent to the decimal number 5. And notice what happens to the decimal weights. They just double every time. 1, 2, 4, 8. What would the next one be? 16, 32, 64. So this is what we would call a 4-track or a 4-channel absolute encoder. So you notice this would be 0. Well, look at this one there. So the 1's covered up, so that would be that code right there. So if I was at this position, if this is where my sensing head was, when this thing rotates, when it got into this position right here, it would say it's at position 1. Okay, now look at this. This would be a 0. So this would be 1, 2, 4, 8. So right here, this would be a 2. This would be a 0, 0. So that'd be a what? 2. Here, this would be a 0, 0, 1, 1. So I'd add 2 and 1. That would give me a what? A 3. This is 0, 1, 0, 1. So I'd add 2, 4, and leave these blank. So that would be a 4. But what you have to understand, this guy is attached to the unit that's in motion. And every time it moves, it comes up and gives a binary code that represents its position. And this is called an absolute encoder. 4 channel. Usually they'll come in a head. So there you go. That would be the light sensor. So the encoder would rotate through this thing, and this would have one pair. So I don't know if you can see it goes under the bottom. Can you see that? So it goes over the bottom. This is the top. And so how many channels it is would be represented. This guy here would pick them all up. It looks like, well, yes and no. We would have to see basically what that head has in it. We can't say it's 5 channel because it's 5 channel. Just because you have 5 pins, it would never work, because you got to have, when you hook up a light emitting diode, first of all, we can't put it directly across the line. But what I have to do is I have to have power for the diode, and that's not a data pin. That's a what? Power pin, right? Okay, so, and then I got to have this right here before I can do anything. So we would have to have power right here, and then we would have to have a common. Well, that's 2 pins right there. Well, you can't say it's 5 channels when 2 of them, we got to have 2 of them for what? Power. So we can't see down below if there's more pins. There might be another set coming out down here that we can't see, because if I understand what I'm saying. So I don't know what channel it is. And there might be electronics in there that takes in the head where we power it up, and it might take 15 LEDs and convert them over to a serial representation of that. Understand? So this guy right here could actually be an electronic device. Well, not necessarily. It gives us a set of 1s and 0s that represents a position. Could be binary, or a lot of them are what we call gray code, which we'll have to look at later on. We have a problem with binary, especially when we're counting it. Yes, that's what. I don't know. Usually when we talk about binary, when we're talking about a number system, that means the digits hold a weight of 2 raised to some power. So the way a weighted number system works, and this works for any numbering system, we start off with digits. And then then we raise base to the 0 power, base to the first power, base to the second power, base to the third power, base to the fourth power, base to the fifth power, base to the sixth power, base to the seventh power. That is a numbering system. So any base you can deal with, you can have a numbering system, because they all follow this weight right here. So if it's binary, then what's the base for binary? 2. So this digit right here would hold the weight of the base, which would be 2 to the 0, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, 2 to the sixth, 2 to the seventh. If this is base 10, this would be 10 to the 0, 10 to the first, 10 to the second, 10 to the third, 10 to the fourth. If it was base 8, it would be 8 base. But this is, when we say binary, it's base 2. So you can't say it. So then we have what we call codes. What is a code? It's when we use something to represent something else. Morse code is a perfect example. We use a bunch of dots and dashes, and those dots and dashes represents all the letters of the alphabet, right? We have the ASCII code, which is a binary code. It's not a binary number system. It is a code. So when you say binary, it's okay, but you got to understand the difference between the binary number system and a binary code. So we have a lot of stuff out there that don't use the binary number system. It uses a binary code. That makes sense? So the problem we have with binary, if we have a term called propagation delay. Well, propagate means to move through, right? Well, the problem is when we do binary numbers. So when I go from a 0 to a 1, how many digits changed? How many digits changed? 1. When I go from a 0 to a 2, how many digits changed? 2. When I go from a 0 to a 3, how many digits changed? 1. When I go from to a 4, from a 3 to a 4, how many digits changed? 3. So the number of propagation, the propagation delay, how long it takes to propagate through the electronics, varies with the number. And we don't like that. We would like to have a constant propagation delay, right? So that's why we use a lot of codes and stuff like that. When it changed from a 1 to a 2, I was kind of set right. There's 2 bits that change. This was a 1, now it's a what? 0. Right here. So originally, this right here was a 0, 1, and this right here was a 0. Well, now this is a 0, so it had to change, and this 0 changed to a 1. Well, the two changes. So if you've got bits going from a 1 to a 0, that's a change. You got bits going from a 0 to a 1, that's change. Okay, so when I look at this one, this is going from a 3. Well, this was a 1, now it's what? Yeah, this is 1, is now what? And this is a 0, now it's a what? 1, so we had 3 bits change. Right? So when I go from a 7 to an 8, we're going to have a 4-bit change. Yeah, the 8-bit changes to 1. So that would be the worst case. But you got to understand, if we're using more than a 4-channel, encoder, you know, if you're using a 10-channel encoder, then there's a lot of bits. So the propagation delay would change depending on the count, and we don't like that. So we'll use the code, which is what we'll get into here. But this is pretty easy to understand, right? So what I could do is, how many positions could I represent with this 4-channel absolute encoder? Which would be 16. So we could see one was at 16 different. Well, what if we needed 53? We're in problems, right? You understand? Because so one of the problems with the absolute encoder is 360 degrees is basically what we got if it's a rotary absolute encoder. So how would I increase the resolution? Add more rings. Yeah. So if we came in here and add another ring, then all these rings are going to get closer together because the resolution is better, right? You understand? But if I added another ring, then that would jump us from 16 to 32. So a 5-band would get 32, right? A 6-band would be what? 64. A 7-band would be 128. An 8-band would be 256. But as we get more bands, then the bands get closer because the resolution goes up, right? You understand? Everybody understand? Resolution is a term we use for basically preciseness, how precise things are. And you see the resolution. Most computers give you the ability to change the resolution of their screen. You know, so you go out and buy a TV when it says 1024 by 768. What are they giving you? Well, they're giving you the resolution of the screen. It's basically a preciseness. So low res, you can't say is how precise things are. So if you say something is low resolution, that means, so you see this all the time when you hit a video on the internet and you can actually see the pixels, a little square box. So they're sending it to you at a low resolution because it's faster to send low resolution images than it is to, it's just like we compress everything now. And of course, one of our main compression formats is what they call a JPEG. I can't remember what JPEG stands for. Well, that's nice, but if you're in photography, if your camera takes JPEGs, you're going to convert them. The first time you use them, you're going to convert them into a high resolution image, like a TIFF file or a bitmap file or a PNG file. Because if it's a JPEG, if you load it in and you edit it, and then you save it again as a JPEG, it's going to recompress it. And so the more times you edit a JPEG file, the worse the resolution is going to be. Most cameras take JPEGs now because why? Because they occupy a lot less space. And what it is they store codes that represents color. So if you got a lot of rolls that has a lot of pixels that are the same color, instead of putting the codes for every pixel, they say, okay, repeat this code this many times. That makes sense. So it's a good format. MP3s, MP4s. Good gracious, if it wasn't for those, there wouldn't be anything like DVDs. You think about storing a whole 3-hour movie on 4.5 gigabytes worth of space. That's not much. So we compress everything. Okay. Now, what's nice about these things is that we can turn the power off of them, and we come up and we turn the power on. It knows exactly where that unit is, even if power's been turned off the encoder. Because if I turn this thing off and it was down here at position 4, well, when I turn it back on, it's still going to be at what? Position 4. So this is the biggest advantage of an absolute encoder, is that, number one, is that we can remove power and turn power back on to the encoder. So the encoder don't hold the position, right? You understand? All the encoder does is gives us the position. Yeah, retentive or non-volatile, or we use a lot of terms in computer. Non-volatile is a term we use for it maintains its content even when power is removed. A volatile is a term we use in computers. That means if you take power off, then everything's going to be lost. But we're limited to the number of to the length, right, or the number of rotations. Even if it was a linear encoder, eventually the linear encoder is going to have to come to an end, right? You understand? So absolute encoders have a range. We can spin this thing forward. We can spin it backwards. It don't make any difference. This guy here has no problem with that at all. Are we okay? We don't have any absolute encoders around here, but you can buy them. Normally, this thing comes sealed up, so I mean, we could look at the internet, and you can't actually. So you could just search for absolute encoders. And you can see the way they come. So let's just look at the images. You can see this guy. These guys, the band gets so small you can't even see them. But this looks like it's a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 band. So that'd be 2,048 positions that this guy here could represent. But you can also see they're basically the same, and they give you a code. They either give you a binary number or they give you a binary code that represents a position. Normally, the ones you'll see will probably look like this, right? You want to actually be able to see the encoder, but you need to know what an absolute encoder is. I don't know if they show any linear absolute encoders in the images. See, this is don't have to be plastic. They actually etch it a lot like they make printed circuit boards. So they'll coat like a piece of plastic with the metal, and they etch off that. These would be a lot. No, they don't. I don't see them showing any There we go. So this would be a linear encoder. Sort of like a barcode, but it would give you ones and zeros. So if the light was coming through, that would represent or one. You have to understand, light coming through doesn't necessarily mean a one. It could be like on the encoder we looked at. It could be just as well as a zero, right? It's just like if I put a glass up here. Binary, we represent binary with two states. And it's up to the electronics and the people who design it what represents a one and what represents a zero. So I could put a glass up here and I could make it full or empty. Well, which one's a one, which one's a zero? Yeah, you have to know. You have to know that. But, so this would be a linear absolute encoder right here. Well, what's nice about these things? This is probably not right. We'll simulate an absolute encoder. Well, what's nice is that the computer or whatever's reading this thing to get the position, if the power goes off and you power back up, it can read that encoder and know where that piece of equipment's at, right? You understand, even though it's been turned off. So these guys don't have to find zero; they know where zero's at. That makes sense. They don't have to find zero. And like when if you got a printer at home, and what does it do when you turn it on? Yeah, you hear it. What do you think it's doing? It's finding zero. We don't hear that much in laser printers, but if you got an inkjet printer, that inkjet printer has to find zero. But it's really, really accurate. That thing understands where it's at all the time. Most people have inkjets at home. So you okay? This makes sense? This is a few problems that we have. These just have to be very precise if your sensors are out of line. So this is why normally we don't use individual sensors. We buy these reading heads where everything is perfectly aligned, so you don't get this bit error right here. Not perfectly aligned binary absolute encoders can create errors. So this is counting in binary. Here we're using 5 digits. Of course, binary, we don't call them digits. What do we call them? Call them bits. So we'd say this is a 5-bit number. That's exactly like saying it's a 5-digit number. So with 5 digits, we can have 32 combinations. And there they all are. 0, 1, 2, 3. So here we had a 1-bit change. Here we had a what? 2. Here we had a 1. Here we had a what? 3. Here we had a 1. Here we had a 2. Here we had a 1. Here we had a 4. So you can see the problem when we're trying to keep up with binary, especially when it deals with propagation delay. Now it's real easy to figure out because we can use this 1, 2, 4, 8, 16 code or a decimal equivalence to figure out what the actual code is. But the problem we have is that if we're dealing with electronics, then we're dealing with something called propagation delay. How many combinations? Did we talk about that? You can come up with any base. You can calculate the number of possible combinations. Now, a lot of people don't understand. I say, how many number combinations can I represent with 2 digits of decimal? A lot of people will say 99, but that's not true because they forget about what? 0. 0 is one of our numbers. So the formula is you take the base and you raise it to the number of digits. And this is true for any of any numbered systems. So I could say 10, and how many? And I said 2. This equals to 100. So we would have 100 combinations if I use 2 digits of base 10. So here we're not using base 10. We're using what? Base 2. How many bits are we using? 1, 2, 3, 4, 5. So I say 2 raised to the 5th, which would be equal to what? 32. So that's the number of combinations we could represent. Now, I know a lot of this off the top of my head because I've been dealing with binary for a long time, right? Probably longer than some of y'all have been alive. So, and I can see the numbers in my head. But that's okay. But this is any. Which one? Right there? Huh? That's 37. No, that's not 37. I'm sorry. That's what I'm doing is I'm seeing this as hexadecimal. 1, 2, 4, 8, 1, 2, 4, 8, 16. So in my head, I'm doing 16 plus 5, which would be 21. I had my mind 5 bits, 32, but I remember it's always 1 less than the number of combinations. So what we do is a code is when one thing is used to represent another. Y'all understand that? The predominant codes used in binary are ASCII, which is the American Standard Code for Information Interchange. This is an 8-bit code that we can use to represent numbers and characters. I don't think I've got that in here, but I mean, it's still available. We're still using the ASCII code today. It depends when it displays the characters, when it displays the codes, probably ASCII code. If you go up to the movie The Martian uses ASCII code. I saw a movie. What was that? What was that movie? Where it was ASCII code, where they said, "Well, this is an older code." Well, this code has been around. The ASCII code stands for the American Standard Code for Information Interchange. No, the keyboard uses what they call a key scan code. But it is a code. We can look up the key scan code. It is not the ASCII code. It's a key scan code. Just doing it by software. And an open. This one detects both the closed and open. So this is ASCII code. This is in decimal. Let's see if we can find one that's in binary. Normally they don't use binary. It takes up a lot of space. That's decimal. Okay. This is in 3 different bases. This is decimal. This is a number system called hexadecimal. That's what was his name did. on the Martian. He used hexadecimal. Hexadecimal is a way we can represent very large binary numbers. We're not dealing with bases. But this would be the binary code. So down here, this is, and you see here's all the characters. So there's the number right there. This represents the what? Yeah, this is the number 0. Which they said was the number. This is base 16, which would be this number right here. So this is the binary code in base 2 that would represent the decimal number 0. But this is a code. So instead of me trying to send, so what you got to understand in computers, computers only understand ones and zeros. But we got to deal with other things besides numbers. Yeah. No, this is ASCII. Yeah. People say ASCII 2, but there's no such thing as ASCII 2. So ASCII stands for this, American Standard Code for Information Interchange. And a lot of people jump on that and say that's a 2, but it's not. Now, a lot of ASCII codes don't use binary because what we need to do is, and we're not teaching this in this class, but just to give you a feel for it, binary is very inefficient as far as trying to give numbers to me. So what we do is we can use another numbering system to represent a binary number. So I could come up here and I could write down, I could write down B6A9. Now, how many people could get that right? If I say, okay, B6A9, how many of y'all could write that down? No, I'm just giving it to you, B6A9. How many could write that down without any problems? Okay, so this is what that represents. That's binary. That's binary. So how many, if I come up and I said 1 0 1 1 0 1 1 0 1 0 1 0 1 0 0 1, how many could have got that number right? Nobody in the class. But if I said B6A9, just me saying it, I say those at the same speed, everybody would get the B6A9 right? You understand? Very few would get those binary numbers because those ones and zeros start doing what? They running together in our head. So normally what we do, or what computers do, computers can make things appear like they're not really are, right? You understand that? So how do we display these images? How are these images being displayed up on the screen? Ones and zeros. We turn a pixel on, we turn it off, and we tell it what color to do it in. Okay, y'all understand that? But the colors are represented with binary numbers. So what we've got is we send a binary number into the display controller. That display controller, if I send all zeros, then the pixel would be what? Off. If I store a binary number in there, it tells the computer what color to display that pixel. It turns the pixel on, but it displays it at a what? A certain color. So all you're seeing is a bunch of little old tiny squares that we call pixels. That's what you're seeing. Well, the computer don't care about the computer does not care about hexadecimal. The computer does not care about base 10. The computer does everything in binary. But when I display stuff up on the screen, all I'm doing is turning pixels off and on, which is ones and zeros. So the computer can display ones and zeros and do the English can display the English language but it don't know the English language. It just knows when I type on this keyboard, we have what we call a key scan code. When I hit the A button, it sends a binary code into the computer that represents the letter A. It runs through a program. The program sticks up these dots up there on the screen to display the what? What I see is an A. But the computer don't know an A. The computer knows a code that represents a keyboard, right? You understand? And these keyboards are soft, that we call them soft keyboards. So the A key don't always have to represent an A. You know, if I'm flying an airplane, I can hit the A key and it might change the ailerons or lower the flaps or lower the landing gear, because all it is a code, and it's up to the program running at the time to determine what that code is. This is I don't know what the key scan code is for the Apple computers, but it is. I don't know the codes. So when I come up here and I take my finger and I touch my screen, it's a sensor there that senses the location of my finger on that pad, and then that sends a binary code into the computer that represents that position, and then the application that's running your phone at the time interprets that code. So that means in 1 minute I could touch on an A key, the next minute I could be pointing out who I want to shoot at, right? You understand? Because it's nothing but what? Ones and zeros. Key scan code. There it is right there. And so here's the key scan code for a standard PC keyboard. And this is not exactly true, because you get one code if the key is pressed. You get one code if the key is pressed without the shift. You get another code if the key is pressed with the shift, right? You get a code when it's released. You get a code when it's pressed. So it's pretty complicated. But this is nothing but, and of course, they don't give us the codes. This is decimal. So when I come up here and I hit the Alt-Shift key, then this would be the sequence of codes that my keyboard sends into my computer. And then what does that mean? So what does Alt F1 mean? Well, it all depends on the program that's running at the time. So we could make that code, it don't get Alt F1, it gets a binary code that represents Alt F1. And then it's up to these programmers to take that dang code and do what you want that computer to do. That makes sense? So what we're doing is we use tons of codes, even now. So when I type something up here, I'm getting a what? A code. Yeah. When I come up here and insert a symbol, and when you can insert the characters too if you want to. When I say symbol, the alphabet's up there too. I didn't want to do that. More symbols. This is the code. And of course, it gives us the code in hexadecimal. We use a code now called Unicode. The problem with ASCII is ASCII was an 8-bit code, which gives us 256 characters in the Latin alphabet. Well, how many countries out there don't use the Latin alphabet? A lot of them. So what they did is they came out with a code called Unicode, which is a 16-bit code. Well, actually, it's more than that, but basically it's a 16-bit code that gives us 65,536 characters, which is basically every language that's available on the earth that we know about now. So that means I used to, if you got a website, if you went to a website, it was English because they used ASCII code. Now you can go to a website and it could be any language, right? You understand? Because they're using a code called Unicode. But if I go back to my Latin alphabet, which is up here at the top, and I go to the number 0, there it is, 30. So the ASCII code is still a subset of Unicode. So there it is, 30. Because they couldn't do away with ASCII because there was a lot of websites out there that was the HTML code was actually ASCII. And if they did away with ASCII when they came out with Unicode, that means all those websites wouldn't work anymore. And of course, this is hexadecimal. And that's what it says, Unicode. So when I come up here and get a key, and I'm using Microsoft Office, I don't put the letter A into the document. I put the code that represents the letter A, and that's what's saved on there. Plus, basically it goes code and then it goes attribute, so we get two codes. So one code would be the code for the 0. The next code would be, okay, how big is it? Is it italics? Is it so that way? So basically, every character gets two codes. So we got off on a lot of stuff, but it's interesting to know. So what they did is they came out with a counting code that we call the gray code. Now this is a code. The only way you can count in this guy is if you've been dealing with Unicode for a long time, or if you look at a chart. So ASCII, I know the codes from 1 to 0. I know the codes for the alphabet, but I don't know the codes for a question mark. So if I wanted to find the code for a question mark, then I would look it up on a code chart. Was it a Christmas Story where he's waiting on his Ovaltine decoder ring? Everybody's seen that. They show that thing every Christmas. Everybody's seen that, Ralphie? Drink more Ovaltine when he decodes it with his decoder ring. But he's having to use a thing that does what? That says, okay, this is what this represents. So notice, this is a 0. I go from a 0 to a 1, which looks like binary. We okay. This is a 2. Well, in binary, this would be the weight of a 3. But what I'm trying to look at is this is not the binary number system. This is a binary code. So how many bits did we have changed from a 0 to the gray code for a 1? How many bits did we have changed from a 1 to the gray code for a 2? 1. How many did we have changed to a gray code for a 3? How many to a gray code for a 4? Gray code to a 5. So what they're saying is the gray code gives us the same propagation delay. Let's go from a 5 back to a 4. We still only have a 1-bit change. So no matter what direction we go in, when we're counting with the gray code, we only have a 1-bit change. So we only have a propagation delay every time. The propagation delay on every count would be what? Would be the same. Does that make sense? Yes or no? But this is not a number system. It is a what? Code. This is a counting code, and it's used a lot. So when you get an absolute encoder or an increment encoder, it probably usually tells you if it's gray code or it's binary. Now, no matter which one you go, I mean, you can look all day long. Of course, we only did 5 bits, and I couldn't even go to 6. I mean, I don't know the gray code. But I know it's a code, and I know I need to find the chart that tells me how to uncode it if I wanted to troubleshoot this thing, right? That makes sense? Okay, gang, I'll take a break. Okay. So this is our little transceiver unit right here. And Ozar will wait until we get through proximity. And you can probably look at one of them's got E for emitter, and then it's got D for detector. Can you see? Y'all can't see it up here. Yeah, y'all can see. And of course, it's polarized, so we have to be pretty careful on how we hook this up. It's a DC device. We don't put AC on these. But what happens is when my encoder wheel comes up here and rotates, what does it do? If I can get my hands out of the way. So it would go between the slot, and when it rotates, what's it doing? It says letting the light pass through or not pass through. So we'll see if we can set up a lab where we do this. Ozar will let y'all spin it. We won't put it on the motor because last time I checked, we didn't have any motors that fit this shaft right here. It's got two sizes, depending on which side you go, but neither one of our motors would fit in this. But this is pretty close to an incremental encoder. But you can see if we had two receivers, we could set one here and set one there, right? You understand? So one of them would be lined up. When I started off, it would, every time this one's on a light one, the other one would be on the what? The black. And of course, if I spun it one way, then one of them would pulse before the other one. If I spun it the other way, then the other one would pulse first. And then I could use whichever one pulsed first to indicate what direction. This transceiver right here, it doesn't have two. It's just got one LED in it, but we could spin it through there and actually see it pulsing. If you did it real slow, you could see it with a meter. But the best thing to do is to look at it with an oscilloscope. So we'll play around with the oscilloscope, or I'll play around with it. We don't really teach that, but just to see these encoders work. By the way, the faster they pulse, then if you put a DC meter on it, the average voltage would actually change. So the slower they pulse, it would average out to a smaller voltage. The faster they pulse, so you could tell. You could see a DC output depending on the speed. So the faster it would go, the more DC you'd get out, right? And so you can tell if they're working with a DC meter or not. But if you actually want to see it work, then you're going to have to use a device called an oscilloscope, which actually shows you what's there. So a meter's nice, but a meter averages everything, right? So a meter is not showing you what's there. It's giving you an average of what's there. So if it's got a pulse stream coming out, all these incremental encoders, it's not going to show you the pulses. It's not going to show you the duration of the pulses. What's it going to do? It's going to give you a DC average. No, it's average. So it's just like me taking a bunch of numbers, and I don't ever see the numbers. All I see is the average. So my meter would show a 6. Well, what's the 6? Yeah, so if it's over here changing like this, right, and my meter shows a 6, then there's not actually a 6 there. It's the what? It's the average. So it's just like you averaging a bunch of numbers. When you see the average, if I've got an average of 6, what does that tell me about the numbers? Well, it don't tell me anything about the numbers. It tells me the average of the numbers. Everybody understand that? Well, okay, there it is. So this would be an example of a subscript. So what's my meter going to show me? So that's what's actually there. I need to maybe. Oh, y'all can't see that. It's got a. Yeah. There's my hand. Okay, so we're going to put it over here on DC voltage. What's that? Yeah. Oh, I thought you said AC. Okay, and what we're going to do is we'll take our DC meter and we're going to hook it up to the output. So this is the if I can get this thing. Yeah, so I could actually turn it down. Let's see if it's still working. Oops. Sorry guys, lost my grounds. Or my common. Meters don't have grounds, they have commons. It's actually showing a negative DC for that. The meter is not going to. Oh, I'm sorry. This is by default. This guy right here puts out AC, so that's why we're seeing negative. So you can see the output of my meter does change. But it's still a lot. It's still an average. And this is AC, so notice when the negative pulses get bigger. So this is the problem with the DC meter. A lot of times we can tell things change, but we don't know until we get a device called an oscilloscope. So that's the advantage of an oscilloscope. What does it do? It shows you what's there. A digital meter is going to do what? It's going to give you an average of what's there. So, but a lot of times when you see it do that, you can get a pretty good feel. By the way, if the frequency changes, I wasn't changing the frequency. If the frequency changes, the meter would probably give me the same average, and we'll talk about that. Okay. So all I have here is I have a bunch of turns of wire. Okay. And then what I'm going to do is I'm going to put my AC on this guy right here. So what determines the amount? This one. There we go. So all we have here is just some wires. Now what I'm doing is I'm putting AC. Now why AC? Because AC creates motion. Because the magnetic field, when it puts current through the wire, creates a magnetic field, builds up, and then what does it do? Then it collapses down, then it changes direction. So if I bring another wire in contact with this, I don't know if you can see this or not. Oops. At least it was working. So what am I doing? So we're reducing in voltage. Without a connection. So there's no connection between this and this. Now what determines the amount is how close, how we called it the coefficient of coupling, how much magnetic field we can couple from my primary over to the secondary. So what do we use to concentrate magnetic fields? So when I come up here and look at this transformer, which is nothing but doing the same principle, I come over here, I see this big chunk of metal right there, because what does metals do? Metals concentrate magnetic fields. Ferrous metals, aluminum works crummy. So if you can't pick it up with a magnet, then it wouldn't concentrate a magnetic field, right? Y'all understand that? So this is solid. This is what we call an E core, which means I got another bar that runs through here. And then your secondary and your primary are wound on top of each other. And you can actually see the wiring. Can you see it? Okay. We okay? And they're literally round on top of each other. Then they use this big old chunk of metal to do what? Concentrate the field. By the way, this is what we call a laminated core, because these are conductors too. And if we used a big chunk of metal, then we would have, our transformer would basically act like a short circuit. So what we do is we divide all these conductors up in here into little insulated plates from each other. So that means the voltage induced into each plate don't add up. Does that make sense? But if I was to come over here and take out the core, then I would get a different voltage on my output, then I would get a lower voltage, right? Y'all understand that? Yes or no? That makes sense? So how conductors is close together because of the amount of insulation on this wire. That makes sense. So that means in plus I can't couple them all together, because if they were wound on top of each other, we would have a lot better coefficient in coupling. And then the thinner the insulator is, the better the coefficient of coupling we have. So this is called magnetic wire. Oops. So basically it's coated with an insulating paint. That's the insulator. It's literally painted on there. Well, we got to be real careful, right? Y'all understand that, because once we wound it into a loop, then the voltage is divided across the length. It's pretty neat the way it works. So if I was to take these two coils of wire and I was to come in and I was to put magnetic wire and wind them on top of each other, then I would get a higher output. But I still wouldn't get maximum, because we have all this air where the magnetic fields go through. So what we do, we put metal in the center, and we call it the transformer's core. So that transformer core, instead of all these magnetic fields flying all the way out here, it concentrates them and makes sure the magnetic field from the primary gets almost over 90% of the field into the secondary that's generated in the primary. So we have this core right here. If I took the core out, I'd still get coupling, but my output voltage would drop right down, and the resistance of the transformer would go way, way, way up. So that's why I couldn't run a light bulb on this thing. That's why I'm running a light emitting diode, is because I have a very poor coefficient of coupling. Y'all understand that? So if I change the coefficient of coupling, then I can change the output of the transformer. Now, if we take two transformers and we wire them correctly, we can wire transformers in